All right, so today what we're going to do is we're going to look at the last type of graph in this section. Then we're going to spend the rest of the time looking at some applications and looking at past exam questions so that you can relate the way they ask the question to the information that you already know. Okay? So let's just talk about exponential graphs. The first thing I want to do is just kind of remind you of the types of graph we've worked with. We have linear graphs. Remember, linear graphs are simply straight lines, and they either go up or down. Up if the x is what? Positive. Down if the x is negative. You can also have the two special cases. If it's flat, what kind of line is that? X equals or y equals?
Y equals.
Y equals, yeah. Then you can have straight up and down, which is x equals. Right? Remember those? So they just equal some number. Okay? Then we started looking at the quadratic. And the graph of a quadratic is called a parabola. And they either open up if your x squared is positive or down if your x squared is negative. Seems like a long time ago when we introduced those. Good morning. All right. Now, today what we're going to do is we're going to look at graphs of exponentials. And the graph of the parent graph, these are called parent graphs when you just see the basic form, and then they can move all over the place, right? But they still maintain the basic form. The parent graph of an exponential is almost like half of a parabola. Not quite, because they're flat on one end. So let me show you what I mean. So it goes like this. Or if it's negative, it goes like this. Or well, never mind. Don't ignore that. I'm so stupid. They still go like that. If it's negative, they go like this. Down. Okay? I don't know what I'm drawing. Okay? Now, the basic way to graph one of these is by simply plotting points. Because when you change the exponent, it changes things significantly on your graph. These things can go very fast. They can go very slowly, depending on what you're doing with them. So they can take lots of different shapes. But there are a couple of things we want to talk about with these exponential graphs, okay, that are slightly different from the other graphs. And we're also going to look at how you can use what we already know in order to graph part of it. Again, you're still going to have to find another point. Remember the parabolas? If we could find the vertex, then we just needed one other point, and we could graph it because of the symmetry. Okay? Well, here we can find one point and then use some other point, just any x value, to find another point and be able to graph it with one other piece of information. So we're going to be doing kind of the same things. And also, you remember that format. You have like an x plus a number in a bracket. What happens when you take that number out of the bracket? Changes the sign. And what does that do to the graph? That's a translation either right or left. And then if you have some number added to your x, or then what happened, or your bracket, what happened? That shifts it up or down. Those rules never change, right? So you're going to still see those for exponential graphs as well. So you're going to use that same information. So keep that in mind as we go. Okay? So we're going to just pop to the book and look at a few of these, and then I'll point out some information. And there's one little weird thing that also happens with these, but it's super easy. You don't have to worry about it at all. Okay. So exponential graph, y equals p to the x. So notice that your x is now in the exponent. And that's what an exponential graph looks like. So your unknown x is in the exponent. So for example, draw the graph of y equals 2 to the power of x. Right? So you see what they look like. So now we have our x is actually in the exponent of the equation. And if you see, they just made a chart, and you could choose any values for these charts. And I'll tell you why they chose some of them in a moment. But here they just did these numbers because these would be demonstrating symmetry if you had a parabola. But exponential graphs do not have symmetry. So the amount that it goes up on this side never matches the amount that it goes down on this side. So don't start assuming that it's going to. It's totally different. Okay? You're also going to see, if you see on the x-axis here, it's difficult to see in this, but if you look in your book, you'll see that this is colored green, the x-axis, because all exponentials have values that they can never be. Okay? So I'm at 62. Okay? So there are some values that they can never be. And those are called asymptotes. Right? And asymptotes are easy to find because they're always that plus c bit. That's where the asymptote is going to be located. Okay? And in this case, there is no plus c, so that means plus what number? 0. And that's why the asymptote is on the x-axis. So what if it was plus 3? Then the asymptote would move up 3 points. Right? So this time, instead of the vertex moving, it's the asymptote that's going to move, depending on your c. Okay? So that's the only huge difference between these. So it can approach this line, it gets infinitely close to the line, but it never crosses it or touches it. Okay? So this can never be 0. There's nothing, in other words, there's no exponent you can put on a number to turn it into a 0. An exponent of 0 turns it into a what? 1. And any other number is going to just turn it into a number, either a fraction or a whole number, right? So there's no exponent that can turn this into a 0. Now, if you had something added or subtracted, then it could become 0. And that's why your asymptote moves around. Yeah? Yes?
The asymptote is always like x equals c, right?
Yes. So say, for example, we had y equals 2 to the x minus 5. There's a horizontal line at negative 5, then is your asymptote. Every time.
It would never be like y equals c. It's always x.
No. Yeah. It's always after the x. It's always added to or after your exponential with your x.
But I mean the equation for the asymptote line itself.
Well, yeah, this is the equation of the exponential will never be an x equals. Your x's will always be in your exponent.
Yeah, no, but I mean for where the asymptote line is.
Mm-hmm. Could you have a vertical one? Is that what you're saying?
Yeah.
Okay. Yes, but not for us.
Yeah. Okay. So for us,
You could have vertical asymptotes. That's very weird. You can also have what are called oblique ones that go at an angle, but you won't hit to that till you get to calculus.
Is it always going to be an asymptote?
Yes, for every exponential there's an asymptote, because for every exponent there's some values that it cannot be.
So for every exponential jump, it's never going to cross the x-axis.
Well, no, the asymptote can move. So, like for this one, for example, if you look at this one, what is the plus c in this one? It's negative 5. That means down here at negative 5, there's an asymptote. So it's always this thing that's added to your exponential term. So what if it said 2 to the x plus 3? That means there's an asymptote at plus 3. It's the easiest part of the graph. Okay. Right? So there's always an asymptote. Yes?
the line will never get straight, right? It'll just keep getting like smaller.
Yeah, it looks like it gets straight, but it just gets closer and closer and closer to that asymptote and never touches it. But
How does it
just, pardon me?
How does it never touch it? So it just end up going straight.
Just closer and closer and closer and closer and closer and closer and closer. So it's never quite straight. It keeps going down just at infinitely tiny amounts. Right? Because think about the numerical system. There's always a number between. Our numerical system is called dense because there's always another number between, right? It can get tinier and tinier and tinier, but there's always another number between any two numbers. Okay? So you can continue to get tinier and tinier and tinier. So in other words, a decimal with, 5 million decimal points is possible, isn't it? Okay? So that's what happens. Now for us, we don't care. We just need to be able to get that basic shape, right? So that we can answer questions. Exponentials are often happen in applications when you're talking about things like interest on money, that kind of thing. Remember that had an exponent has an exponent in it. Some exponential, this is exponential growth. You've heard that term before, I hope. So you'll see some of those. So you'll see some applications with these. Now, a couple of other things, right? These can be, so this is the basic parent graph where the asymptote is at 0. Notice our y-intercept. Where is it in this particular graph? At 0, 1. It's always true. The y-intercept is always 1 unit above the asymptote. Now, except we can have shift, right? Vertical, we can have those translations, so keep that in mind. Okay, so we'll talk about these patterns because remember, just like the quadratics, you can use patterns to, if you know the parent graph, you can then use patterns to move these. Now, these other points that they've used, you're on your own. Just choose a point, plot it, just like we did with the parabola, right? We just need some other point to show us where the curve is going. And we typically pick points on this side because we know what this side's doing. What's this side always going to be doing? Going down and approaching the asymptote. Who cares? And it's always going to be weird, funky numbers. You don't care, right? So on this side, don't worry about values unless they ask you to find a particular value. You don't care. Because if they ask you to find a particular value, then you have to either plug in y or x and solve, right? But on this side, we need to know, is this one going straight up like this? Is it going wide like this? Or like the parent graph going up like this, right? So we need to see what's happening on that side only. Does that make sense? Because this side's always doing the same thing, just going down until you hit the asymptote and just follows along it. Okay? So you do not need this many values. But they're just demonstrating some things here. And we need to talk a little bit about the laws of exponents, just so you'll remember them. So if x is 3, 2 to the third is an 8, right? So we started to the power of 2. That's that dark line, the solid line there, right? That's the one we just looked at. If you have it 3 to some power, look what happens. It goes up much faster, right? And then 5 to some power is up faster still. Okay? Now, I'm going to tell you that they're only going to use, when you're looking for the equations, because we're going to eventually have to find the equations of these from the graphs, they're only going to use 2s and 3s, because if you get to other powers, it becomes really difficult to do. Right? So they are at least nice to you there when we look at the powers. But you can see they just use the same exponents and again, just demonstrating. And why do the asymptotes stay the same?
Because there's no added number.
Yeah, there's no number added to your exponential term. Okay? All right. If that's the case, if your asymptote is 0, do you notice anything about the y-intercept? 0, 1. Okay? Because anything to the power of 0 is 1. Right? So if your asymptote is 0, so in other words, if there's nothing added or subtracted to your term there, then that point is always going to be your y-intercept. Makes it very nice. Now, and we also know the rules for shifting that, for translating it. So if we can translate, if you can remember that for the basic graph, it would be here, and then you can learn just how to move it by using the B and C rules that we've already done, those translations, then you can always find the graph. And it's always going to be based on this, in this case, it's always going to be based on the asymptote. Okay? And again, I'll show you what I mean by that when we look at some more complex graphs. So here we go. Here's our first translation. So we have y equals p to the x plus or minus some c. Remember, for exponentials, the c is just your asymptote. So it's just going to move the asymptote up and down. But if the asymptote moves up and down, then that means the whole line is going to also move up and down. Yeah? Because remember, it's always going to be 1 unit away from that asymptote at some point. Okay? So look at what happens here. So we have y equals 2 to the x plus 1. So this plus 1 is going to shift my asymptote up 1 unit from the axis. So you can go ahead and put that in first, always. Okay? So when you're doing these, first, put in your asymptote. It's the easiest part to find because it's always your plus or minus whatever is at the end, either up or down. Okay? Then, if you use a translation, right, for these, what did we do to the asymptote? We moved it what? Up 1. But there's no x plus or minus, right? Do you agree? Okay, so there's no b. There's just a c. So we had a translation up or down, up in this case, right? But no translations right or left because we didn't add or subtract anything from our x. Do you remember those points? So all it does is shift everything up 1. So instead of 0, 1 as our y-axis, what do we have? 0, 2. It just shifts it up 1 unit. Everything just shifts up 1 unit. Now, we still have to find some point out here because that's 2. You could do a shift if you memorize that 2 to the 3rd power is 8, so it's going to move up to 9. But if you don't want to memorize that, just choose another point. Okay? So if you memorize 2 to the x, then anytime you add or subtract, you can just move it up 1. And that way you don't have to work out another point. So for example, if we did this for y equals, I put too much stuff on my graph, I can't see. 2 to the x, okay, hold on just 1 second. 2 to the x, okay. If we put in 3 in place of that, that gives us y to the 8 plus 1, which is, y to the equals 8 plus 1, which is 9. So in other words, 1 more than not having the plus 1, which makes total sense, right? You're adding 1. Yes?
If the coefficient was 1,
Mm-hmm.
how would that?
Don't worry about it. It's not going to happen. If the coefficient is 1, everything you're going to get is a 1.
Yeah.
So it's not going to happen to you.
But it would just be like a vertical line. It would be like x or y equals.
Yeah. So you get you get a line. Don't worry about that. Yeah, that doesn't. The smallest coefficient, the smallest base for your exponent you're ever going to have is a 2. Okay? Now, it can be negative, but that just means that instead of going up, your line would go under the asymptote. If this was negative. Okay? All right. Let's look at what happens. So here, again, we're just adding the 1, so that just means it shifted everything up 1. So if you remember that 2 to the 3rd is 8, 2 to the 3rd plus 1 is going to be 9. So if you want to work it out, it always works, right? Just choose a point and work it out. Or if you want to remember the graph for 2, then as long as this is a 2, right? If that changes, then all bets are off. So it's easier just to pick a point. But the main idea is this point, that if your asymptote moves up 1, your y-intercept moves up 1 as well. Okay? All right. And we'll finalize some steps in just a second. I just want you to see every case. Okay. So this one, 2 to the x minus 2. So where's your asymptote? At negative 2, right? Okay. And where's your y-intercept going to be?
Negative 1.
Okay. Because it's always 1 above. Unless it moves right or left. In this case, there's no right or left movement because we have 2 to the x. Not 2 to the x plus 5 or 2 to the x minus 3, which you will have in a minute. Okay, so in this case, you just have vertical shift.
So the y-intercept is always 1 above the asymptote.
Well, in the basic graph. So let's look at what happens here. Okay, so there's the basic graph. Okay, so filling in the points. Let's just look it up. So if it's 2 to the 3rd minus 2, that gives you now a 6, right? So 3, 6 is your point. So that's right there. But again, yeah. So do you see what's happened? Is this y-intercept has just moved down 2. Everything just moves down 2. And again, if you memorize those points, you can just subtract 2 from them. But it's always 1 above in the basic graph, right? And the reason for that is that's where 0 is. And so the only way you can get a 0 is if that's anything to the 0 power is always going to give you a 1. Right? And then the other part's just going to move it up or down. Okay? All right. So there's a pattern to these, just like the others. Let's look at what happens. Okay, so they give you some of those where you're just graphing those. What's the asymptote here?
0.
What's the asymptote here?
Negative 4.
Just -4. Yeah. So do you see how easy it is? Right? So now, you can also get shift to the left or the right. So another translation. They call that translations, right? So remember what happens when you pull that 1 away from that x in the bracket? Turns it into a -1. It always changes the sign when you take it away from 1. So the same thing. So remember, like we had y equals x plus 2 quantity squared. When we pulled that away, it turned it into a -2. Yeah? Well, the same thing is going to happen here. So when we have y to the 2x plus 1, when I pull that 1 away from that x, it's going to make it -1, which means that it's not going to shift to the right one, but to the what? To the left one. Okay? So everything's just going to shift to the left one. Now, does that affect my asymptote?
No.
Okay. So, look at the graph. Asymptote is at 0. Okay? Now, all the points move to the left 1. Okay? And they have 2 graphs on this one, so don't pay attention to some of the stuff they have on there. So the basic graph of 2 to the x would be just an asymptote there. Your normal point would be there, but here everything is just shifted 1 to the left.
Why is it this random? Is that an asymptote line then?
So,
That line there, yeah, what's that doing?
yeah, I'm not sure why they have that there. Let's see what they've done here.
Compare this with the graph of
Why are they putting that there? This is right neatly and everything. So since your C was 3, it went up 3. Since your B is -1, negative because you pulled it away from the x, which changes its sign, that's left 1. So you'll see that they went from the parent graph. If you just know the parent graph, it makes your life so much easier. It means it went left 1 and up 3, so that puts that known point there. Now we still need another point, okay? And since our known point is over here to the left of 0, we could use 0, but you really want to point over here somewhere to show you what the curve is doing. Because if you just had these 2 points, let me show you. If you have that point and that point, does it tell you what the curve is doing toward the end? No. So you would move over here somewhere. Now, be careful, though, with exponentials. What happens with exponents? They get big fast, right? So don't choose something over here at 4. Never use 4. It's too big, always, right? 2 to the 4th power is already 16. That's big, yeah? We don't want that. So use 1 or 2. In this case, 2 already falls off the graph as well because of your...
No, it's at the very top of the graph.
Well, is it right there? It's a little higher. So that's why they've used 1.
Two's just below.
Is it?
11 and the graph is
2 is 11? Okay.
11.
That's not.
Yeah.
I don't know. She said it is.
Yeah.
I trust her. Let's see what it is. Oh, well, here it is. 2. 2 is 11. Yeah, she's totally, absolutely right. So it would be at the very top. But you don't know that till you do it. So frequently 2 is too big. Okay? So if you have something added here, stay small, right? Especially if you have add 3 as well, right? Because that's going to move it even more. So 1 or 2 at the biggest would be enough to give you the graph. Okay? And that's true of all of these. Don't get carried away. So use 1 or 2. Now, again, they're not going to give you the nice chart for yours. You're going to have to do that for yourself. Okay?
What's the left side of the graph? How do we make sure that the graph is actually properly because it's all those fractions?
We don't care. Just draw a line that goes down like that.
Does it not have to be super accurate?
Don't care at all. It's remember, when you're drawing one of these, it's a sketch anyway. You're never going to get it perfectly accurate. Pardon me?
What if it actually accidentally touches the asymptote? Will they take points off?
Just be careful.
Too big.
Just try to be careful. Okay? All right. So, let's write some steps, guys, because we like steps. To graph exponentials. First, okay, find the asymptote. It's a horrible word, okay? And that's always that plus or minus c. Do I change the sign for the asymptote? No, whatever it has, that's what you use. So if it's plus 5, it's on positive 5. If it's minus 3, then down 3, okay? Second, okay, think of the parent graph where y-intercept is always 0, 1. Oops, sorry. Don't put y equals y-intercept. Sorry, I said it, but I didn't write it. The y-intercept is always 0, 1. Right? That's the parent graph. That means there's nothing added to either you don't have a B or a C. Okay? So that's no B or C. Knob or C. That looks terrible.
So you have to do the parent graph.
Well, you don't have to draw it. You just have to think it. Because that's where your shift is going to come. Right? So it just makes it easier. You could just choose a bunch of points, but this is a lot easier than choosing a bunch of points. Right? This narrows it down to 2 steps, just like the parabola, we have 3 steps. Okay? Then, translate up or down, and left or right. Again, that's all about your B and your C. Right? Your B is the thing that's added to the X. When you pull it away, it translates either to the left or right. Okay? Then plot that point.
So why do you define the graph first?
From, pardon me?
Why do you define the parent graph first?
Well, because if you can count that point from the y-intercept. So you're not plotting the parent graph. You're just thinking of that one specific point on the parent graph. It's always 0, 1, right? And that 0, 1 is going to tell you, you're going to move from there. Because usually when we do our B and C, we're moving from the origin, right? But this is, on exponentials, they're different. You're moving from the y-intercept of the parent graph. And that y-intercept is always the point 0, 1. So that's why it's a big deal to think of the parent graph. Good question. Okay? Then plot, okay, let me put that a little bit differently. Then plot one more point. And you usually use x equals 1, x equals 2. Don't get too big. Okay? Because if you get bigger, because it's an exponent, if you get big, then the exponent, the number gets really big very fast. Plot one more point. One more point, PT.
If the graph is negative, do we want to graph pick a negative point? Maybe.
No.
Yeah, okay.
Because remember, it just moves it from left to right. So the x can be positive, and that's fine. You're just going to get a negative value. Right. Okay? All right. There, and then, of course, draw your line. And again, remember where it's approaching the asymptote, just let it go down there. Who cares? You're never going to get it perfectly right because you can't even graph those fractions. You have to guess when you're graphing a fraction in the first place, yeah? And at that point where it turns, everything under that is going to be a fraction. Okay? Because that's the point where your exponent equals 0. Okay. Does that make sense? You want to practice a couple of them? So let me give you some of these that you can practice. And you don't need to do all of the ones that they have in the book. It's not going to help you that much. But what I want you to do is I want you to do some of the plain ones. And then I want you to concentrate, though, on the ones that actually move away, because that's going to be more common. But you're going to have to be aware of the plain ones as well. So let me just stop the recording.